Welcome to Lesson Up, math tips, tricks, and other ideas. To help continue expanding this site, please don't forget to subscribe and like. One of the more common types of probability problems are birthday problems. They come in a lot of varieties, but one of the most popular birthday problems is the birthday paradox problem. In essence, it states how many random people are needed in a room so that it is greater than 50% that at least two of them share a birthday. Now, there are some things to consider. We go on the premise that there are 365 days in a year, so this will exclude leap years, and we go on the assumption that any birthday is equally likely to occur as any other birthday. The reason this problem is known as the birthday paradox is because its results are counterintuitive to what we would expect. So there is something else to consider, which I call the handshake scenario. Suppose there are 10 people in a room, and each person was to shake hands once with every other person in the room. How many handshakes would occur? Well, person 1 would shake hands with person 2, then person 1 would shake hands with person 3, then person 1 with person 4, and then with person 5, and of course, this pattern would continue until everyone has shaken hands with everyone else in the room. So though we may have 10 people in a room, there are 10 choose 2, which is 45 handshakes, that occur. To put this in practical terms, there are a lot more occurrences than there are individuals. The birthday paradox has the same logical concept, but rather than people sharing handshakes, they're sharing birthdays. So the solution may seem small to what we would expect, but that is due to the illusion of the number of occurrences that could happen. Now, this problem is not as sophisticated as it may present itself if we keep our ears peeled on what is being asked. And to me, a big red flag is the phrase "at least," which summons the complement of a probability. Now, I address complementary problems in some of my other video lessons, so you should check them out if you would like to learn more. But I like problems that have complementary phrases, because these phrases guide us on how we should proceed in our calculation. We approach this problem by determining the probability that none of the people in a room share the same birthday. For example, if we have 2 random people in a room, whatever the birthday is for the first individual, the probability that the second person does not have the same birthday as the first person is 364 out of 365. Placing a third random person in the room, the probability this person does not have the same birthday as the other 2 is 363 out of 365. Adding another person, and the probability that this person does not have the same birthday as the others is 362 out of 365. This pattern continues every time a person is placed in the room. By the time we have 6 people in a room, there is approximately 96% probability none of them will share the same birthday. Now, this probability will get smaller and smaller every time another person enters the room. The dilemma is how many people must enter the room to satisfy the problem. Notice that the pattern that develops for the numerator of the proportions is a permutation of the form 365 permutate r, in which r is the number of people in a room. The denominator of the proportions would be 365 raised to the r power, again where r is the number of people in a room. Since we are utilizing the complement, we simply subtract this value from 1, and the result must be greater than 50%. And voila, this is the inequality that models the problem. Now, as any student of counting techniques understands, permutations and powers inflate very quickly, so the use of a strong calculator or computational program needs to be used. We then experiment with different numbers of people in a room until we zero in on the smallest number of people that results in greater than 50%. If we run the numbers, we see that only 23 people are needed in a room in which there is greater than 50% likelihood at least 2 of them share the same birthday. Again, this seems counterintuitive, but if we go back to the handshake scenario, if there are 23 people in a room and each has to shake hands once with every other person, there will be 253 occurrences of handshakes. Considering this makes our results a lot more plausible. So if you want to have some fun, if you're in a classroom with 30 students, there is almost a 71% chance at least 2 students will share the same birthday. Give it a try. To help continue expanding this site, don't forget to subscribe and like, and we'll see you next time.